This is number 37 on page 187. And basically we have a particle here that's 215 grams. Now we need to change that to kilograms, of course, because that's not SI. It's released from rest at point A in a hemispherical bowl of radius 30 centimeters. Calculate the potential energy at point A relative to B. And so let's do that. Well, it's released at point A, and since this is hemispherical, that means the distance from the center of this particle to here is going to be the radius of the ball, which is 30 centimeters. So we're going to write down here potential energy equals mgh. Of course, this is gravitational potential energy. So that's going to equal 0.215 kilograms. We have to change grams to kilograms. That's 5,000. We can use 10 here, 10 meters per second squared. And then h is 30 centimeters. Change that to meters, 0.30 meters. And so when we put that in our calculator, we get EEGA equal to 0.645 joules. All right, now it wants us to calculate the kinetic energy at B. Now this is A, so B. But here is where conservation of energy comes in really handy, because kinetic energy is equal to 1/2 mv squared. But see, energy is conserved, it just changes form. So up here it has 0.645 joules of potential. Well, it has 0.645 joules of kinetic down here, because this is my 0 point here. In other words, I'm measuring from here, so this is 0. Up here is going to be my 30 centimeters, right, or 0.3 meters. So when it goes from here to here, all that potential changes into kinetic, and so I don't have to do or find the velocity or anything. It's just going to be 0.645 joules, and that's going to be the kinetic energy right there. Okay, and then C, so we just found kinetic energy based on the fact that we know that potential here is equal to kinetic here. So the C part definitely makes sense in that we can find the kinetic energy now. I mean, the velocity. Because we know the kinetic energy is 0.645. That's the total energy all the time in this, because this is frictionless. And that's going to equal 1/2 times 0.215 kilograms times v squared. When I work this out, it's going to be 2 times 0.645 divided by 0.215 kilograms. I'm going to take the square root. I'm going to get v equal to 2.45 meters per second. So I'll circle my answers here. Here's the answer. Here's the answer to A. All right, and then D, D is going to be find the potential energy at C. Well, we know the total energy is 0.645, so I know the potential energy can't be that because it doesn't make it back up all the way to here, right? Doesn't make it all the way back up to there. So it's going to be mgh, just like before. Whoops. mgh, not mgg. mgh, which is going to be 0.215 kilograms times 10 meters per second squared times h, which is 2/3 R. So that's going to be 2 times 0.3 divided by 3 is going to be It's going to be 0.2. Is that right? 3 times 0.3 is 0.6 divided by 3 is 0.2. So it's going to be, height here is going to be 0.20 meters. That's 2/3 times 0.3 meters. So if I put that in my calculator, 0.215 times 10 times 0.2, I get 0.3. So my answer here is 0.43 joules. 0.43 joules. Now, how do I find the kinetic energy? This is PEC. Well, KEC, basically what we have here is the total energy at C is going to be PEC plus KEC. Well, we know PEC is 0.43. We know total energy is 0.645, so we just say 0.645 minus 0.43, and we get 0.215. So this would be, when we rearrange this, it's going to be 0.645 joules minus joules minus 0.43 joules, and that's going to equal 0.215 joules. So the E part, let's find the velocity. So that's going to be KE equals 1/2 mv squared. Let me extend the page here. And so I'm going to say 0.215 joules, right? That's kinetic energy, equals 1/2 times the mass, 215 grams, 0.215 kilograms times v squared. So if I just do 0.215 times 2 divided by 0.215, take the square root of that, and I get 1.4. So velocity equals 1.41 meters per second. That's velocity at C. So let's circle my answers here. And this is the answer here.